Hey there, it's Shannon Matchick-Myers, and today we'll be covering section 13.4, Differentials, from the Larson and Edwards calculus text. So we will be looking at the concepts of increments and differentials, extending the concept of differentiability to a function of two variables, and using a differential as an approximation. So let's take a look at a Calc 1 problem where we look at the possible propagated error in computing the area of the square. So if you remember how to do it, go ahead and pause the movie and warm it on up. 1, 2, 3, you can do it. All right, let's see how you did. If we're taking a look at a square, right? So with this square, remember, of course, that the area of a square is equal to the side squared. So we have our function at s plus delta s minus our function evaluated at s is approximately equal to our delta a. So that delta a is the propagated error . That's delta A. And then S itself is going to be the measured value. And then if you take a look at delta S, what you're going to have is your measurement error. All right, so what we have for this S plus delta S is going to be the exact value, whatever that is. So of course there's going to be human error and measure, whatever you're using as a measurement tool will have some error. So these are all the things that are going on. Now it turns out that, and this is all things that you would have developed in your Calc 1 class, but it turns out that this delta A can be approximated by dA, and dA is going to be equal to, and that's again approximate, f prime at our s ds. So I'm using the notation that we've got here. Our f of s is equal to s squared, and so our dA will be approximately f prime at s ds. Cool so far? So continuing, we will get dA will be 2s ds. Good so far? And then we will have what? Well, let's check it out. What were we given? The measurement of a side of a square, so the measured value, S, was equal to 12 inches, right? Possible error of a 64th of an inch. So possible measurement error was ds. Sorry, we're having some construction done. And that's going to be plus or minus 1/64th of an inch. So let's take a look, plugging this information in. So our dA would equal to 2 times 12, right, times plus or minus 1/64th. So let's see what we've got going on. We've got dA would be 24 times plus or minus 1/64. 8 divides both of those, so dA would be, if we divide out an 8, we'd get 3 here and 8 here. So our possible propagated error in the measured area, or in the area given these parameters, would be plus or minus 3/8 of an inch. Cool so far? So putting that in words, we would say, in our conclusion, the possible propagated error in computing the area of the square is approximately plus or minus 3/8 of an inch, and sorry, that's area, so it's in square inches. Cool so far? All right. So now, so this here had, S, where S was the measured length. Okay, so definition of a total differential. If z is equal to f of x and y, and delta x and delta y are increments of x and y, then the differentials of the independent variables, x and y, are dx is equal to delta x, and dy is equal to delta y. And the total differential of the dependent variable z is del z is equal to, and remember we have to use the curly d, so del z, del x, dx, and then plus del z, del y. Well, that in turn would be equivalent to fx of x and y dx plus fy of x and y dy. Okay? So let's find the total differential here. We've got z is equal to x squared times y. So what would we do? What are we going to need to find? Good. We're going to need to find zx. So zx, if you remember from before, will be, good, we treat the y as a constant. So 1 over y times 2x, which in turn would be 2x over y. And then zy would be what? Awesome. The x squared would now be treated as the constant. And then we've got y to the negative 1, so we'd have negative y to the negative 2. And so that in turn would equal to, good, you would have negative x squared over y squared. Cool, cool? So our total differential is going to be, so del z will be equal to 2x over y dx, and then minus x squared over y squared dy. Cool, cool? All right, awesome. So let's take a look at the next one. So now we've got a function of x, y, and z. So we're going to need to find wx, the first differential of w with respect to x. So we treat everything as a constant except for x. So the derivative of cosine of x with respect to x is, awesome, it's going to be negative sine of x. So we'll have negative e to the y sign at x, and the z squared term zeroes out. Wy is going to be equal to, beautiful, it's just going to be e to the y, because that's the exponential is its own derivative, and we're doing it with respect to y, so if you apply the chain rule on the angle, you would just get 1. And then cosine at x goes along as a constant multiplier. Now wz, the very first term zeroes out, and then we would just get 2z. Cool so far? So the total differential of w is going to equal to negative e to the y times sine at x, and this is just regular dx, okay? And then plus e to the y cosine at x dy plus 2z dz. Good so far? Awesome, awesome, awesome. So now, let me box that one up. Let's talk about the definition of differentiability. So a function f given by z equals f of x and y is differentiable at x0, y0 if delta z can be written in the form delta z equals fx of x0, y0 times delta x plus fy of x0, y0 times delta y plus epsilon 1 times delta x plus epsilon 2 times delta y, where both epsilon 1 and epsilon 2 approach 0 as delta x comma delta y approaches 0, 0. The function f is differentiable in a region R if it's differentiable at each point in R. Okay? So, now, let's take a look at another example. So let's find z equal to f of x and y and use the total differential to approximate the quantity. Let's check it out. So first of all, what would f of x and y be? Beautiful. You're going to have x squared 1 plus y cubed. Cool so far? Fx of x and y will be 2x times 1 plus y, the quantity cubed, and fy of x and y will just be x squared, and then 3 times 1 plus y, the quantity squared, times 1 using the chain rule. And then that cleans up as 3x squared times quantity 1 plus y squared. Cool so far? Now, our 2.03 is exactly 2 plus 0.03, which gives us our x plus dx. And then our 8.9 is equal to 9 plus negative 0.1, which would be our y plus dy. So this here is our delta z, which is exactly equal to f at x plus delta x, comma, y plus delta y, minus f of x and y. So that would be the total differential of z. But remember that we can approximate delta z as approximately as what? dz, and that would end up being fx of x and y dx plus fy of x and y dy. So we'll have dz will be equal to our fx of x and y was 2x times 1 plus y, the quantity cubed, times dx. And then our Fy was 3x squared times 1 plus y, the quantity squared, times dy. And then putting those values in, we'll have our total differential of z will be 2 times 2 times 1 plus 9, that quantity cubed, times 0.03 for dx, plus 3 times 2 squared, 1 plus 9, the quantity squared, and then our dy was negative 0.1. So here we go. Wherever there was an x, I put in a 2, right? And wherever there was a y, I put in a 9. And then we had, let's see, we had our dx was 0.03, and our dy was negative 0.1. Cool, cool? All right, so doing some computation, we will have 4 times 1,000 times 3 over 100, right? 300ths. Plus, let's see, we'll have a minus 12 times 100 times a 10th. And so some of this will divide out. This 100 will divide out all but 10 of the 1,000. And then this 10 will divide out part of that 100. So when we simplify, we would get dz is 40 times 3 is 120, and then minus 120. So dz, the total differential of z, actually ends up being 0. Cool, cool? All right, so next up is a theorem, sufficient condition for differentiability. So if f is a function of x and y, where fx and fy are continuous in an open region R, then f is differentiable on R. Okay? So what is that saying? Your premise is that you've got this continuity, right, where your first partial derivatives, fx and fy, are continuous. And if that's the case, then f of x and y is differentiable, right? So now, then we come to the theorem, differentiability implies continuity. So if a function of x and y is differentiable at x0, y0, then it is also continuous at x0, y0. So we have this one before, right? So, so here we go. If we take a look at the proof of this, what we would want to do is, the premise is that f is differentiable, right? So let's let f be differentiable. At x0, y0. And we're going to have z equal to f of x and y. Cool so far? So if that's true, then what do we have? We have delta z is equal to what? Because f is differentiable, right? So the definition of differentiability, we're going to use right here that, we're going to use this in our proof. So what that means is that delta z would be equal to fx of x0, y0 times dx, delta x, sorry, plus fy at x0, y0 delta y, and then plus epsilon 1 times delta x plus epsilon 2 times delta y. But how could we rewrite that? Let's rewrite that where we put the delta x's together and we put the delta y's together. So I'll factor the delta x and delta y out on the right. So that would give us fx of x0, y0 plus epsilon 1 times delta x plus quantity fy at x0, y0 plus epsilon 2, all of that times delta y. Cool so far? All right, awesome. Now, remember with this definition, said that what? Both epsilon 1 and epsilon 2 approach 0, right? As delta x comma delta y approaches 0, 0. Cool? But by definition, what do we know? Isn't delta z also equal to f of x0 plus delta x, comma, y0 plus delta y minus f of x0, y0? We're going to let x equal x0 plus delta x, and we're going to let y equal y0 plus delta y. And equating the two expressions for delta z, let's see what we'll have. Well, the one from substituting would be what? X, we said, was going to be x0 plus delta x, right? And we also said that y was going to be y0 plus delta y. All right, so putting that into the equation, what are we going to have? We would end up having f of x and y, right, minus f of x0 and y0 would equal to fx of x0, y0 plus epsilon 1 times delta x plus fy of x and y plus epsilon 2 times delta y. So we just equated this equation with the substitution to this equation here. Cool, cool? Okay, so, all right, over here, if x is equal to x0 plus delta x, then wouldn't delta x equal to x minus x0? And similarly, delta y would be equal to y minus y0? Cool so far? So, substituting that stuff in on the right side, this would end up being fx of x0, y0 plus epsilon 1 times x minus x0 plus y of x0, y0, plus epsilon 2 times y minus y0. Good so far? Now, taking the limit, right? If we take the limit as x and y approaches x0, y0, let's see what we're going to have, right? So we're going to take the limit of this expression here. So we have our fx of x0, y0 plus epsilon 1 times x minus x0 plus fy of x0, y0 plus epsilon 2, all of that times y minus y0. And what will that limit end up being? Well, as x approaches x0 and y approaches y0, with direct substitution, what would happen? That limit's going to be 0. So therefore, we can conclude that the limit as x and y approaches x0, y0 of our f of x and y is just going to equal to f of x0, y0, right? And I'm looking here at this one because if you take the limit of both sides as x and y approaches to x0, y0, you'll get that that limit approaches f at x0, y0. And what does that imply? That means that f is continuous at x0, y0. And we're done. Cool, cool? Okay, so let's take a look at this third example. So another triangle one. A triangle is measured and two adjacent sides, adjacent next to each other, are found to be 3 inches and 4 inches long with an included angle of pi over 4. So if we just take a look, something like this, right? We don't want to assume it's a right triangle. So let's say that we've got this angle here as pi over 4, and then we can say that this side would be 3. We can say this side could be our 4, right? And so A would be 3, because those are the measurements, and we could say B is 4. Now the possible errors for each of the sides are what? Beautiful. This dA, you know, that's fine. This dA is equal to dB is equal to plus or minus a 16th. So kind of like that other problem, right? And then as far as the angle, right, what were we given for the angle? So if we call this angle, you know, A, B, and C, right, DC would be plus or minus 0.02 radians. Cool so far? All right, so you can either look it up or whatever, but you've got a side angle side situation. So the area, if you've got side angle side, is going to be ½ times the product of the adjacent sides times sine of the included angle. So we're not going to put in any of the measurements until we actually, you know, do the derivative, right? Let's let the area be equal to some z. dz would be equal to the first partial derivative of dz of z with respect to a times dA plus the first partial of z with respect to b times db plus the first partial of z with respect to the angle c times dc. Cool so far? Okay, so let's find those partials. All right, so I'll do them over here on the side. ZA would be what? Good, it would just be 1/2 B sine C. ZB is going to be 1/2 A sine C, and ZC is going to be 1/2 A times B times cosine C. Cool so far? So, putting those in, we'll have dz will be, I'm going to factor out the half, and then we'll have b sine c dA plus a sine c dB plus ab cosine c. Sorry, dc. Cool so far? Okay, so then dz, plugging in the values that we know, will be 1/2 times, b was what, 4? So we'd have 4 times sine pi over 4 times dA, which will be plus or minus 1/16. And then plus 3 sine pi over 4 times dB, which was plus or minus a 16th. And then plus 3 times 4 times cosine pi over 4 times dc, which was plus or minus 0.02. All right. So let's see, we can divide some of this stuff out. The 4 divides out some of the 16 on that one. That's about it. So now we would end up having, when you simplify, let's see what we get. So dz would be equal to sine pi over 4 is 1 over root 2. This is 1 over root 2. This is also 1 over root 2, or you can say root 2 over 2. And so when I get out the calculator, this is what I got. All right, so we've got 0.5 times sine pi over 4. And then that was divided by 4 plus 3 times sine at pi over 4 divided by 16 plus 12 times cosine pi over 4 times 0.02, which is approximately, let's go one more than our radian measure, right? We'll go to, we get 0.239, so that'll be 0.240, right? 0.240, and that would be plus or minus. It's approximate. And that would be in inches squared, because that's the possible error in the propagated area, okay? All right, so that ties up that problem. And then example 4, show that the function f of x and y equals x squared plus y squared is continuous by finding values for epsilon 1 and 2 as designated in the definition of differentiability, and verify that both epsilon 1 and epsilon 2 approach 0 as delta x and delta y approaches 0, 0. Okay, so let's go ahead and let z equal to f of x and y. And so delta z is equal to f at x plus delta x, comma, y plus delta y, minus f at x and y, kind of like we did in that proof, right? Well, what's that going to be for our particular function? We've got x squared plus y squared, so we'd have x plus delta x squared plus y plus delta y squared. That's for our f of x plus delta x, y plus delta y. And then minus f of x and y is going to be x squared plus y squared. Cool, cool? Okay. So now what are we going to get? Well, we would have, I'll just crunch it all out. We have x squared plus 2x delta x plus delta x squared plus y squared plus 2y delta y plus delta y squared minus x squared minus y squared. So everything, let's see, the x squared 0 out, the y squared zeros out, and then let's see what we're going to have. So we will have 2x delta x plus 2y times delta y plus delta x times delta x, that's how I'm writing my delta x squared, and then plus delta y times delta y. Good so far? And let's go ahead and you know, show that we're grouping these, okay? Because we want to match that definition. So isn't this equal to fx of x and y times delta x, right, plus fy of x and y times delta y? And then what if I were to let epsilon 1, right, be the delta x multiplier, and I'll highlight what I did, and then epsilon 2 be the delta y multiplier. So this is basically letting epsilon 1 equal delta x and epsilon 2 being delta y, right? But I want to match the formula, so I'm only doing it for part of the expression, right? Now, okay, as delta x and delta y approach 0, 0, right? Doesn't epsilon 1 approach 0 and epsilon 2 approach 0, right? So we're done. Cool, cool? All right, so that, I guess we didn't need that extra page. You can have it for a different thing. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, please subscribe and tell your friends. Bye.